When astronomers first tracked 3I Atlas moving toward a region of space dominated by an intense gravitational signature, the mood inside observatories shifted from curiosity to cautious anticipation. This object was already unusual. Identified as an interstellar visitor due to its trajectory and velocity, it did not belong to our solar system and was not bound to the Sun in the way comets or asteroids typically are. Its speed, composition readings, and light curve variations had already sparked quiet debates among researchers, but nothing in the early data prepared scientists for what appeared to unfold next. As 3I Atlas approached a region where space itself seemed distorted by the presence of a suspected black hole, telescopes across multiple wavelengths locked in. Black holes, by definition, do not allow anything to escape once it passes the event horizon. The boundary marks the point where gravity becomes so overwhelming that even light cannot return. Normally, when matter spirals toward a black hole, it forms an accretion disk, a rapidly spinning ring of superheated plasma and debris glowing intensely in X-rays and high-energy radiation. If an object the size of 3I Atlas were to plunge inward, scientists expected a brief but powerful flare, followed by silence as it disappeared beyond detection. Instead, what unfolded was far more complex. As the object moved closer, instruments detected a sudden spike in radiation that did not match typical infall signatures. The energy release was sharp, concentrated, and oddly structured, as though something had disrupted the normal flow of matter within the accretion disk. For a brief window, gravitational readings fluctuated, suggesting turbulence in the surrounding spacetime. Observatories monitoring radio emissions recorded anomalies that appeared synchronized with the object's closest approach. At first, some researchers suspected calibration errors or interference from background cosmic sources. However, independent systems confirmed the disturbance. Something real had occurred near the black hole's boundary, and it was directly linked to 3I Atlas. What shocked scientists most was what happened after the radiation spike faded. Instead of losing track of the object entirely, telescopes began registering a continued mass signature in the surrounding region. The object, or something resembling it, was still detectable. The brightness profile shifted slightly, and its spectral fingerprint appeared altered, but it had not vanished. This defied the most basic expectation. If it had crossed the event horizon, it should have been gone permanently, hidden from the universe behind a veil of gravity. The possibility that it never fully entered the event horizon quickly gained traction. Researchers began examining whether 3I Atlas may have skimmed the outer boundary of the black hole's gravitational well instead. Black holes are surrounded by complex regions beyond the event horizon, including the photon sphere and ergosphere, where extreme gravitational and magnetic forces twist matter into violent motion. If an object the size of 3I Atlas entered the accretion disk at a precise angle and velocity, it could have experienced extreme compression and heating without fully crossing the point of no return. In such a scenario, tidal forces would stretch and distort the object, potentially stripping material from its surface while simultaneously compressing its core. The interaction between the object's structure and the magnetized plasma of the accretion disk could trigger magnetic reconnection events, releasing bursts of energy. This might explain the sharp radiation spike observed during the encounter. But the deeper mystery emerged in the aftermath. Follow-up measurements suggested that the object's apparent mass and reflective surface area had increased slightly. This observation was subtle but consistent across multiple instruments. Scientists had to consider whether 3I Atlas had accumulated additional material during its close encounter. The accretion disk surrounding a black hole is not empty space. It is filled with dense, fast-moving plasma and fragmented matter from previous interactions. If 3I Atlas passed through this region without being fully consumed, it could have swept up material along its trajectory. Under intense gravitational compression, plasma can momentarily bind to solid surfaces, especially if rapid cooling occurs once the object escapes the hottest zone. In other words, the object may have emerged coated in new layers of matter drawn from the disk itself. Another possibility involved relativistic jets. Some black holes emit powerful jets of energy and particles along their rotational axes, ejecting matter at near light speed. If 3I Atlas passed near a magnetic reconnection zone associated with such a jet, it might have been accelerated outward after partial interaction. This would create the illusion of a dramatic plunge and return, when in reality it executed a complex gravitational maneuver within a narrow boundary layer of extreme physics.
Computer simulations soon followed. Astrophysicists modeled scenarios in which an interstellar object grazes a black hole's accretion disk without crossing the event horizon. These simulations revealed that under rare conditions, objects can gain kinetic energy through gravitational slingshot effects combined with magnetic field interactions. While black holes are primarily known for consuming matter, their surrounding environments are dynamic and chaotic. Energy transfer does not always move inward. In certain configurations, matter can be violently redirected outward. The key variable appears to be trajectory. A slight difference in angle, speed, or rotational alignment could mean the difference between destruction and survival. If 3I.Atlas approached along a path that intersected dense plasma at a shallow angle, it may have experienced rapid deceleration, followed by magnetic acceleration, effectively bouncing outward in a process driven by extreme relativistic forces. This would not violate established physics, but it would represent a rare and dramatic case of survival within one of the universe's most hostile regions. Even more intriguing was the subtle change in the object's spectral signature. Light reflected from its surface after the encounter showed minor differences compared to earlier observations. This suggested alterations in surface composition or temperature distribution. If additional material had fused or adhered during the close approach, it could account for these changes. Alternatively, intense heating might have restructured the object's outer layers, melting volatile compounds and reshaping its surface geometry. Some researchers proposed that internal stresses caused by tidal forces may have compacted the object's core, increasing density without significantly changing volume. That alone could produce readings interpreted as increased mass. Yet all these explanations remain provisional. The central tension lies in interpretation. Did 3I.Atlas truly merge with the black hole in any meaningful sense, or did it simply endure a near-catastrophic encounter at the threshold of extreme gravity? What shocked scientists most is that it not only overturns physics, but it highlights how much complexity exists around black holes. Popular imagination portrays them as simple cosmic vacuum cleaners, swallowing everything indiscriminately. In reality, the regions surrounding them are among the most energetic and structured environments in the universe. Magnetic fields twist into spirals, plasma forms turbulent vortices, and radiation pulses outward in unpredictable bursts. Within this chaos, rare interactions can occur that stretch our observational assumptions. The case of 3I.Atlas may represent one such interaction. It reminds scientists that survival near a black hole is not impossible under every condition. Rather, it depends on precise dynamics and timing. As data continues to be analyzed, astronomers remain cautious in their conclusions. No one claims that the object entered and exited the event horizon in defiance of relativity. Instead, the focus has shifted towards understanding the boundary regions where gravity, magnetism, and plasma physics intersect. Whether 3I.Atlas absorbed matter, experienced extreme compression, or merely reflected transient radiation in a misleading way, the encounter has already expanded scientific discussion. It forces new simulations, new observational strategies, and renewed attention to the environment surrounding black holes. And perhaps most importantly, it serves as a reminder that the universe rarely behaves in ways that are simple or predictable. In the brief, violent dance between 3I.Atlas and a gravitational giant, we witnessed not a contradiction of science, but a deeper glimpse into how extreme cosmic systems truly operate. As the initial shock settled and the raw data began transforming into structured analysis, the scientific debate shifted from what was seen to what it truly meant. Black holes, according to Einstein's general relativity, are absolute in one crucial respect. Once matter crosses the event horizon, there is no return, no signal, no fragment, no information escapes. This principle is foundational to modern astrophysics. So the central question quickly became unavoidable. Did 3I.Atlas actually cross that boundary, or did it only appear to? The distinction is everything. Most researchers now lean towards the interpretation that the object never passed the true event horizon, but instead entered a region just outside it, a chaotic zone where gravity is overwhelming yet not final. Surrounding a rotating black hole is an area known as the ergosphere, where space-time itself is dragged along by the black hole's spin in a phenomenon called frame dragging. In this zone, objects cannot remain stationary, they are forced to move with the rotation of space-time. If 3I.Atlas entered this zone at a specific trajectory, it could have been violently accelerated, its path bent in extreme arcs before being flung outward again. The physics of such interactions are complex but not impossible. In fact, theoretical models have long suggested that energy can be extracted from rotating black holes under precise conditions through mechanisms like the Penrose process. While this typically applies to particles rather than large interstellar bodies, the underlying principle remains. Near a black hole, energy transfer does not strictly move inward. In certain configurations, matter can be violently redirected outward. The key variable appears to be trajectory. A slight difference in angle, speed, or rotational alignment could mean the difference between destruction and survival. If 3I.Atlas approached along a path that intersected dense plasma at a shallow angle, it may have experienced rapid deceleration, followed by magnetic acceleration, effectively bouncing outward in a process driven by extreme relativistic forces. This would not violate established physics, but it would represent a rare and dramatic case of survival within one of the universe's most hostile regions. Even more intriguing was the subtle change in the object's spectral signature. Light reflected from its surface after the encounter showed minor differences compared to earlier observations.